Sigma times an eigenvector is equal to lambda eigenvector. If I'm going to pick a single direction that will return the largest vector back, and then I'm going to take the dot product itself to get the magnitude, I would need the eigenvector with the largest eigenvalue. And at the heart of it, that's actually why the eigenvector with the largest eigenvalue is the direction along which you get the greatest variance. So you can either spend a little time thinking about that and understand why that's true, or you can believe me. I guess I could have written it out more, but I think most of you at this point know that I take the eigenvector, the largest eigenvalue of the covariance matrix, that's the direction of the greatest variation. So that's what this says here, that the direction that captures the maximum covariance of the data is the eigenvector corresponding to the largest eigenvalue of the data covariance matrix. Ta-da! That's what we're doing. So, furthermore, that's the longest one. I can take the top, I don't know, k of them, orthogonal direct, and they're all orthogonal to each other, and that will capture the most variation that I can of k orthogonal vectors. So I could say, well, I've got this 10,000 dimensional thing, maybe I'll take the top 10, 20, 30, 40. That captures as much variation as I can with 10, 20, 30, 40 orthogonal vectors. So that's what I want to use. But in order to do that, in order to do PCA on images, I have to teach you a trick. And this is the PCA for D, much, 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 much bigger than M or N trick. All right. And so let's do the trick. So here's the dimensionality trick. All right. And the notation that I'm showing you here comes directly from the paper Turk and Penland, I'll mention it later, that does eigenfaces, but it'll be clear. Let's suppose that this cap phi I is a face image. So it's really long, right? D long. And by the way, let's assume we've subtracted the mean. Okay, so we've actually removed the mean from all the pictures that we have, and so we've got the mean at the origin. Fine. All right. So now let's define a new matrix called C, which is just the average of phi, the sum of phi transpose, okay? This is the sum of all the outer products, and in fact, this can be written as A transpose if A, this is just what it says here, is just the stacked up face images, right? So A, it's the stacked up face images, it's going to be D, really big, by M. M is however many face images I have. So it's huge by reasonable. That's what A is, and that means AA transpose. So if I take D by M times M by D, I get a what? D by D. All right, D by D. That is a really big matrix, okay? So if D was 10,000, this would be a 10,000 by 10,000 matrix. How big is that, Megan?
A lot.
That's a lot, exactly. That's 100 million, okay? So if it was a million long vector, a D by D would be a million times a million, which would be a million million, which is a big number. That's 1,000 billion, which is a trillion. That's a lot. You wouldn't ever want to do that, okay? The idea of trying to find the eigenvectors of a 10,000 by 10,000 matrix is painful, even on today's computers, and of a million by million matrix is even more painful. But fortunately, you don't have to. So C equal to AA transpose is a huge matrix. But now, instead of considering A transpose, consider A transpose A. That's only an M by M matrix, right? Because remember, A is D by M, so A transpose A is M by M. Finding the eigenvalues and eigenvectors of that, pretty easy. Well, suppose I've got some eigenvector VI that's an eigenvector of A transpose A. So if it's an eigenvector of A transpose A, that means when I multiply A transpose A times VI, I just get some multiplier, lambda, of VI, the eigenvalue. Pre-multiply that equation by A. When you do that, now I've got AA transpose, and I made this blues to make the difference clear, AVI. And by the way, I just pulled a lambda out on the right-hand side. It's just a scalar. I can do that. Look at that equation. What do you see? What do you see? What do you see? What you see is that the AVIs are the eigenvectors of AA transpose. Remember, AA transpose is that big, ugly matrix, C? So all we needed to do was to find the VIs, which are the eigenvectors of the A transpose A, pre-multiply them by the matrix A, and I now have the eigenvectors of AA transpose. All right? So what this basically meant was we took the eigenvectors of an M by M matrix and created the eigenvectors of a D by D matrix without having to explicitly compute the eigenvectors of D by D. This is much easier to compute. Quick question. How many eigenvectors are there? If I had more than D images, okay, so D is 10,000 dimension, let's say, or a million. So if I had, 10,000 images and I was looking at all those, I could get 10,000 eigenvectors. But clearly, the sum of those outer products, if I've only got a small number, right, the whole idea is that M is going to be a lot less than D. So how many of them are there? Well, your intuition might say, well, I've got M independent things, so there must be M of them. But actually, your intuition was wrong. And in fact, a better intuition would be the following. Suppose I give you 2 points in 3 dimensions, okay? How many vectors can span those? Just one, right? I go between them. And the reason is I have to think about subtracting off the mean, right? And once I subtract off the mean, actually I only have 1 degree of freedom, right? Because the origin is going to be halfway between those 2 points. So once you tell me where one of the points is, I know where the other one is. So there's only 1 degree of freedom. So with 2 points, there's only 1 possible eigenvector. Let's think about it this way. If I have 3 points in space, okay, how many vectors does it take to span those points? Well, they lie in a plane, don't they? Of course they do. 3 points defines a triangle. So with 3 points, there's only 2 eigenvectors. In general, there are m-1 eigenvectors. And the reason there's m-1 is I take my m points and I subtract out the mean, so that removes a degree of freedom. So that's a trick question that I always give on the final of my course. So if anybody's taking the final, now you know the answer. Okay, there's m-1. Let's apply this to face recognition, and it's referred to as using eigenfaces. And it comes from this paper by Matt Turk and Sandy Pentland. It's Alex Pentland, but his name he goes by Sandy. They were at the MIT Media Lab at the time. And one of the reasons this paper, besides the fact that it works so well, is just known so well, in my humble opinion, is because of this term eigenfaces and face space. What a great phrase. In fact, I can show you the eigenfaces. I will in just a minute. All right, so here's what they do. They assume that most face images are going to lie on some low-dimensional subspace in the big image space, determined by, I don't know, let's say k eigenvectors, okay, k directions of maximum variance, where k is going to be way smaller than d. So d might be 10,000 or a million. K is going to be like 20 or 200. Both of those numbers are way smaller than 10,000 or a million. So what it does is they use PCA, like I just showed you, to find the vectors, or what are called the eigenfaces, we'll look at them in a minute, U1 through UK, that span that subspace. Okay, so you take all your images, you find your eigenvectors. And now what you're going to do, and this is the really cool part, is you're going to represent your face images in that data set as just the linear combination of those eigenvectors. Or another way of saying it is, I'm just going to have the coefficients of, if it's 20, of the 20 eigenvectors, if it's 200, 200 eigenvectors, and I'm going to represent my entire image, all 10,000 numbers, by just the coefficients of these eigenvectors, and I multiply those coefficients times the eigenvectors, sum them up, that would be my new image. All right, so it's a tremendous data reduction. So take you through an example here. So, and some of these images come directly from the old paper, some from some newer work, but makes the same point. So suppose I have some training images, x1 through xm. So here's a picture of faces. Now notice it's just the cropped part of the face. So they're going to try to do recognition just on the cropped part of the face. So the first thing that's kind of cool to look at is this is the mean image. Mean face, not the mean face, the mean face, the average face. Now nobody wants to have the average face. Too bad. Whoever that is, he or she has the average face. Why did I say he or she? Well, by definition, it's hard to tell, right? Because it's an average over everybody. There is some interesting work done on showing how average faces appear more beautiful than real faces. This was done a long time ago. It was just a study of the appearance of beauty. Anyway, it was an interesting image processing approach to thinking about, could you predict when a face would be deemed beautiful? Right? You can imagine, here's a question. Show a picture to a computer, face image, pardon the digression, and say, on a scale of 1 to 10, how likely are people to rate this thing as beautiful? This person is beautiful. And could you do that? I think these days using machine learning might be a different approach, but at the time there was work done on looking at average faces. Sure, you wanted to know that. Anyway, oh, and so what do you do with the mean face? Like what you should do with a mean face. You throw it away. Well, what you really do is you subtract it out of your population. Isn't that great? We subtract all the mean faces out of the population. No, we subtract the mean face from all the, and what we have left is our distribution. And then we start computing the eigenvectors, and here they are. Okay, so here are some top eigenvectors. And one of the things you'll notice right away, in fact, let's take a look at this first eigenvector, actually the second one, is that it's much brighter on one side than the other because some of the variation might just be due to the lighting coming from one side or the other. But later, you have these different eigenvectors which look like these kind of ghostly images, but these are eigenvectors. So they look to you like pictures, and they are, but what they are is they're a 10,000 dimensional vector, which is just an image. Remember, I can go between the image space, 10,000, right, and the images. So I'm just showing you these eigenvectors as images. Okay, and if I want to take a dot product of a real picture and these, that's easy. All I do is overlay them and multiply. Multiply every pixel and sum them up, because that's what a dot product is. So when I show this to students, sometimes they don't understand how come the images are eigenvectors, and that's because in image space, that's what it means. A vector is an image. So it's a little bit easier to understand what these eigenvectors do if we look at it this way. Here are the principal component eigenvectors, 1 through whatever. Here's 2 different reconstructions, all right? If I take the average face and I just add 3 times, and sigma k is just the standard deviation of the coefficient, don't worry about that. If I take the average face and I add in some of that component, I get this kind of thing. And if I subtract off that kind of component, I get that thing. Notice that that just moved the lighting from the left to the right. So one way of thinking about it is that these components, the first components, just changed whether the lighting direction was from the left to the right. Whereas, let's see, let's take another one. Here, this component here, if I add positive, I don't know, it tends to look a lot more feminine. When I go negative, it tends to look a lot more masculine. Okay? So each of these different eigenvectors are adding in some other different variation, some other different element. So how do you use these? Well, a couple of things have to talk about. First is, I have to be able to get the coefficients. Well, that's real easy, just like I said before. I take in some image, x, here it is, and I just subtract off the mean face, and I take the dot product with, in this case, the first eigenvector, second, third, all the way up through the kth eigenvector. Those dot products will give me these coefficients, or weights, w1 through wk. What's cool is that vector of numbers, just k of them, maybe it's 20, maybe it's 200, that's my entire representation of this face. So I've taken this 10,000 dimensional vector, 10,000 elements, 10,000 pixels, and I've reduced it to 20 numbers. So how do we make use of this vector, these w's that are the coefficients? Well, the first thing is I can actually use them to reconstruct the face, right? Each one of these w's tells me how much of each eigenvector to add back in. And in general, what I can do is I take a picture and I say this picture is represented by the mean plus the each of the w's times the eigenvectors. That's what this is. And if I were to keep a lot of them, I would get a really great reconstruction. If I keep some of them, I get an okay reconstruction. Well, how many of them do I want to keep? Well, remember, I wasn't doing this to do reconstruction. I was trying to do recognition. So how do we do recognition? Well, actually, it's pretty straightforward. I have some new novel X comes in, some new novel face image. All right? All I do is I project it into the subspace. What does that mean? Just like before. I subtract off the means, and I compute the dot product, the coefficients, W1 through WK. By the way, I can then do something that's optional put here. Suppose I'm not really sure that what you gave me was a face image. Well, what I can do is I could reconstruct using those coefficients. And now here's the thing.